Well, I'm broadcasting from beautiful Maui. That's why I'm wearing my Hawaiian shirt. So what I'm going to talk to you today is about how to make AI have a really bad carbon footprint. So where does this thought come from? Well, early in my career, a friend and I thought to teach grad students how to give a good talk. It'd be funny to tell them how to give a bad talk and give them commandments to give a bad talk, and then if they don't want to do it, a bad talk to alternative commandments. And then that was so much fun. I did how to have a bad career, and then another decade or so went by, and then how to have a bad research center. And so this is the fourth in the series, and this kind of documents my kind of tour as I learned about carbon footprint and environmental issues, and I'm going to share what I learned here. Okay, so part one, how to make it bad. Part two, pretty quickly, how to not make it bad. And then I'm going to go into a lot of fallacies that I've learned about and pitfalls that I've learned about the carbon footprint, and see if there's time for Q&A afterwards, and try and keep us on time. So let's do it badly. So pick the biggest model you can. You know, OpenAI said scaling laws work, so bigger is better. The newer GPUs use a lot more power, so use an old one. It's cheaper and less energy, and just use the nearest data center to you. You don't want to have to ship the bits all across the country. So now, we did in one of these papers, we were able to talk about carbon emissions by 4 factors that you multiply together and you get the carbon emissions. The first is the model. Just like prior speakers, we're going to use the Llama model 405B. So 10 to the 24th is a septillion. This is about 40 septillion operations to train. Next is the hardware. We're going to use an older one. Volta was the first GPU with AI accelerants in it, and so we'll use that one. And so that's going to have a energy per floating point operation. So we multiply those two together, and we get the energy to train it. Now, this thing has to be in a data center. How do we measure the overhead of the data center? Well, the industry uses this term power usage effectiveness, which simply, if the energy going to the computers is X, what's the overhead on top of that? So a lot of local data centers, it's factor of 2. So that is as much energy goes to cooling and power distribution as it goes to the computers that run the AI. And that's still, so we get the energy when we multiply the first 3 M's together. Now we got to turn that into carbon. If we want to make it really bad, let's go where they burn coal, like in West Virginia, and then we get the carbon out of that. When you multiply that all together, all 4 factors, you see they get these 240,000 tons, spelled British, which Americans call metric tons. So that's how much carbon emissions to train that Llama model using Voltas and common data centers. What do we do to avoid that? Well, don't do the things on the right, do things on the left. Get the most efficient model, the latest GPU, use a cloud data center. People have been building those for 20 years. The hyperscalers know how to build them with very low overhead. And then as long as in the cloud, let's go someplace that has very clean energy. Okay, put that in. We're going to use a more efficient model. Google has an open source model that takes only 2 septillion floating point operations to train, about as good as the Llama model. So that's a factor of 20. We have data on Trillium, one of the most recent TPUs. That's about in terms of energy for floating point operations, about a factor of 4 better. Like I said, the hyperscaler data centers are very efficient. Has only like a 10% overhead. That's about a factor of 2. And then let's not use coal. Let's use hydroelectric power, which is a factor of 10 less energy. When you multiply all those things together, you get, by picking the 4 M's, you can make it almost 1,600 times better than if you don't be careful about the 4 M's. Okay, so that's just an example. Now, the rest of the talk is going to be this kind of tour I've been on, learning about carbon footprint in about the last 5 years. And I'll show you what I've learned, and hope we have time for question and answers. The first one was, well, what about using the latest, should we use older GPUs or the latest GPUs? So recently, some friends and I at Google did the first what's called life cycle analysis of the carbon footprint of several TPUs. And life cycle analysis means we go all the way from getting the materials out of the ground, manufacturing it, operating it, and even end of life. And so we came up with a new metric that we call compute carbon intensity. And what you can see on the right is 5 GPUs. The 3 on the left get called versatile TPUs. I think of them as inference TPUs. And the 2 on the right are powerful, or I think of training TPUs. And now what you see, these tall bars have different colors to it. The little light blue pieces out at the bottom are the embodied carbon footprint from manufacturing and shipping the things. It's very small for data center TPUs or GPUs because they have really long lifetimes, like 5 or more years, and the data centers are 20 years lifetimes, and they burn a lot of power. So almost all of the carbon footprint is in operating them. And then you see there's 2 different heights there. So what's going on? So part of learning about carbon emissions is you learn about this accounting mechanisms. I skipped that in the slide, but somebody got me started in this. They said, keep in mind, Dave, energy is physics, but emissions is accounting. And why is that? Because you have these complicated supply chains. Who's responsible for what? How do you know the energy really clean? So there's accounting mechanisms for that. So there's 2 ways to do the accounting. One is if you just get it from the utility, how dirty is the energy that you get? And that's called location based, and that's the tall bar. But they wanted to encourage companies to try and get carbon free energy. So there's also a market base. If you spend money on clean energy, you can reduce the carbon footprint. And that's kind of the medium blue bar. But the good news from our perspective, when we did this study of Google, and we didn't know how it would turn out, is that even though the newer TPUs use more energy and have a bigger carbon footprint, they're so much faster that their carbon intensity, it's better. So fortunately, we found out the best thing from an environmental perspective is to use the latest GPUs. If it turned out the other way, that would have been awkward. But they use more energy, but they're so much faster. That's the best way to go. So that's our first fallacy. These fallacies and pitfalls comes from the book that Henderson and I did in computer architecture. The second one is, again, has to do with this accounting mechanisms. And you can see, to give you a hint, what I'm going to tell you about, it shows a movie set facade. The building looks good in the front, but when you look behind it, it is just empty space and a fake facade there. So to be able to explain what's going on this greenhouse gas protocol accounting kind of gimmick is I'm going to have to tell you an allegorical story. So let's say you and your friend Max, you're single, you guys are roommates, you eat all your meals out. And you start getting worried, eating all your meals out, maybe this is not so healthy for us. You learn that there's this movement underway to try and encourage people to eat organic food. And what they do is they have little symbols on the menu that says organic. And when you order one of these organic meals, you get a little organic certificate. And to encourage people to do it, they have a contest to see who can eat the most organic meals. So you think this is great. Max doesn't really care. You turn yours in and you have 800 organic meal certificates, there's about 1,100 meals a year. And you turn it in and you win. Max doesn't really care. He's only got 100 of them. But you win. And your parents are proud of you, or your friends. You get dates. Big success. You're very excited. Next year you do it again. You realize you better up the ante. So you do 900 organic meals that you order and eat. But when it's announced you're in second place, somebody did 1,000. And shockingly, it's Max. But he almost never orders organic meals. So you confront Max, what's going on? And he says, well, I read the fine print and you have to pay. They count the number of receipts, but you don't have to eat the meals. So I found in San Diego in April for breakfast, I bought 1,000 cheap meals and I turned them in. But you said, hey, but Max, it doesn't help your health. You don't eat organically and you don't even help the local restaurants. You're not buying locally, you're buying in San Diego. And you don't even help San Diego. You're buying all the breakfasts rather than 3 meals a day. He says, well, I don't care. I win. My parents are proud of me. I'm in the newspaper. So what? Okay, so how does that tie into carbon footprint? Well, when they were trying to encourage people to have this marketplace, they tried to set up the ground rules. And how do you know it's really clean energy? Well, they have energy attribute certificates, EACs. And so, like Max, if you buy a meal and eat it, you get one of these EACs, energy attribute certificates. And when you get it, you use it at the same time you buy it, it's called bundled. But in these early days of the greenhouse gas protocol, people said, well, we should be able to do more than that. So they had this idea, well, how about we not when you consume it, but some other time. So I'll just buy the local energy, but I also buy energy, clean energy, another part of your country at another time of year. And those are called unbundled certificates. In fact, they don't even have to be in the same country. Like in Europe, you could be in France, you could buy them from Poland, anywhere in the same time. So that's how it was interpreted. So a bunch of universities studied this, how effective they are in bundled ESAs, and they said not very effective. They may look good on the claims to the companies, but they really don't significantly help because they don't like if you buy the restaurant meals someplace else, it doesn't help the local utilities. If you're buying energy, clean energy someplace part of the United States, the local company isn't incentivized to do anything about it. So, how popular are these unbundled EACs that are misleading? So, this paper came out, and a lot of my studies are going to be for 2023. And here's the top four hyperscalers in the United States. And the second column is their location based energy, and then it's the market based. And you can see, like for Microsoft, it looks like they almost have zero carbon footprint. And that's because half of these are these unbundled EACs. Facebook hardly used these unbundled at all, and Google didn't use any. That was because Google has been promoting the idea of trying to use clean energy 24 hours a day and from the local environment. So that was part of their policy. So although it looks like under the current rules that you can make your carbon emissions go to zero, that's a misleading claim for many of these organizations. Okay. The third fallacy, and you hear that all the time, is that data center AI is a major consumer of global electricity. So my source is the International Energy Agency. It is 60 countries. It's been around for more than 50 years. They're trying to encourage clean energy use. And they estimated in 2022 the data centers were 1.2% of global electricity use. They think for 2025, it's about 1.5%. And they say even with strong growth, they think four things will be much larger than data centers. Just continued economic growth, not surprisingly, electric car growth, they think will be much larger. I was surprised that air conditioners use will be larger than data centers and high energy manufacturing. And keep in mind, there's a lot in data centers besides AI. AI is a piece of it, not all of it. But that doesn't mean, just because it's not a global problem doesn't mean it can't be a local problem. In particular, a lot of these data centers are in small number of countries. So United States, China, and the EU have most of the data centers there. So they can be a local problem, but they're probably not a global problem. Okay. Fourth fallacy, like, well, is this problem in the United States? We just don't have enough electricity to go around. So what the kind of the nuanced version of this is most utilities expect what you want is electricity almost all the time, what we would call 4 nines of electrical availability, so down less than an hour a year. So this graph plots for the top utilities for a given year how much electricity is used. And what Dukestein pointed out, well, if you have to have 99% 4 nines of availability, there's hardly any electricity available like that. But if you were capable of using electricity that had only 2 nines, that you could be down a couple of days a year, there's a lot more electricity that's available. So I kind of illustrated that in the green bar. So for a given infrastructure utilities, a lot of the power that they can produce is unavailable because people expect 4 nines of availability. But data centers like Google say, hey, we can live with 2 nines of availability and get this power. And we'll use batteries or something else if we really need more than 2 nines of availability. But that's available, no extra investment by utilities, they can get more money. So what does that mean? So if you want to lower your electricity bill, try and get a data center that's willing to take 99% of available power, because utilities can kind of get money for free that they're not getting right now. So these lower availability gigawatts really are available today for people who can figure out how to use them. The fifth fallacy is this, this is not very renewable energy, that's kind of this ivory tower stuff. It's not practical today. That's not the case anymore. Solar is the cheapest energy source per kilowatt hour, and it's dropping over time. And natural gas is now the highest, and it's rising over time. And of course, solar and wind have very low carbon footprint, and obviously coal is very high, and natural gas. The seventh fallacy has, I'm going to start talking about water use. And this is where we're going to start getting into examples where a claim gets made. And when we look in more detail, we see these claims are often exaggerated. So it's a paper from UC Riverside that says every user prompt of one of these chatbots uses 7.6 to 47.5 milliliters of water. So supposedly in 10 chatbots, that's a whole bottle of water. Well, that data suggested, where did they get the high end? Well, that was Washington State. And why was Washington State so much higher? That's because it was hydroelectricity from dams. Well, why would hydroelectricity dams have so much water use? Well, it's open to interpretation, but most of that water use is from evaporation. And by the way, these dams are capturing water in Washington that would otherwise go into the Columbia River, go out to sea. But if the water is sitting in the reservoir, it will evaporate. But that was what was being charged for these models. But most of the reason for the reservoirs is not for generating electricity. That's a side effect. The main reason is for either drinking water or for agriculture. So, for example, only 3% of all the reservoirs in the United States have any electric power. That's not the reason they're there. This is kind of, well, as long as we got one, let's generate some power. But they were being charged as if the charge for the evaporation of the water. So we did a study for the Gemini, and in terms of based on the data center use, how much water in the data center was 5 drops of water per chatbot. If we went ahead and did the electricity generation piece of it, like the Riverside paper did, let's say it was used for gas. We use natural gas, and by the way, Google does buy clean energy, which is almost all solar and wind, which has no water resource. So even if we added the electricity use, it would be very small. So we think the real data is about 150 times less than the high end of what the Riverside paper said. All right, so that's the first water fallacy. The second fallacy is these data centers cooling. All data centers must consume water. So there's really many ways to remove heat from a data center. There are these giant air conditioners you can put on top that uses up more electricity, but no water to cool. So that would raise the overhead from about 1.1 to about 1.2 or 1.25. You can also, in colder climates, just suck in cold air up from outside to cool the data center. Or you can similarly, if you're near the ocean, you can use seawater to cool data centers. And evaporative units or the other option that does use water. So you pick the best thing for your geography. If you put a data center region that's high freshwater stress, don't use evaporative cooling. So what Google is, if it's in the center, Google's policy, if you're in a place that uses evaporative cooling and there's pressure on fresh water, invest in other projects that generate more fresh water. So the goal is the net of the investment and the water use is you'll generate more fresh water than you're using. And the goal is in 4 years to be 120% of all water use. And to keep in mind, whenever you hear these numbers, like how much is being used. So it's kind of one of these data centers is like, for 100 megawatts, it's kind of like one golf course. And we have, 15,000 golf courses in the United States and say 500 data centers. And now, in terms of these overestimates, this book by Karen Ho, Empire of AI, which came out several months ago, said in the book, it says this study in South America that a local data center would use 1,000 times as much water as the town nearby, 1,000 times as much. Well, this high school physics teacher tried to figure it out, and they said that couldn't be right. The people drink much more water than that. And he investigated and found out it was off by a factor of 1,000. Instead of liters measured, she thought it was cubic meters, not liters. cubic meters of water. And so it was actually off by 1,000. And so what she acknowledged the mistake, and future editions of the book, when they start printing in the future, they'll kind of make this little tiny 1,000x change in the conclusions. Okay. And the fifth one, the eighth fallacy I'm up to now is that edge AI, well, if it's data centers aren't so bad, what about edge AI? That was a question we got. And so we looked into that. So actually, there's not that much energy use on the smartphones themselves. If you just have a phone, how much is AI? And when we measured it, it was say less than 3%. But almost all of these studies that we looked at ignored the chargers. They just flip the phones themselves. But that doesn't make sense. You only use electricity from the grid when you're using the charger. It turns out, if you just look at the phone, almost all of the energy is the display, the wireless radio, and then the chargers. And the chargers are very inefficient. What we learned was that wireless chargers, which have to be ready to go when you drop a phone in, use much more energy than wired chargers. And often, many people will have multiple chargers and just leave them plugged in all the time. And there's a phrase for that: when you leave something plugged in, even though you think it's off, kind of dead, it sucks electricity even though it's off if it's plugged in. That's called vampire energy use. So to put in perspective all of these different issues here, AI use compared to all these things, particularly manufacturing, we put a little video together that goes along with this paper, and I hope you'll be able to hear that. It's too close.
What is the carbon footprint of machine learning on our smartphones? The good news is that for all of the phones in the world, machine learning adds up to only about 0.3 million tons of carbon dioxide equivalent emissions per year. Pretty small compared to the amount Wi-Fi and the display add. When we add in all the other processes on the phone, we're just over 10 million tons of CO2. Of course, the phones are running on battery power and only drawing electricity from the grid when charging. Wireless chargers are increasingly popular, but unfortunately, they are even less efficient. If we forget to unplug our wireless chargers, they continue to draw power from the grid, like energy vampires, even when nothing is charging. If manufacturers included a sensor that only activated the charger when a phone was present, we could save most of this wasted energy. So is that all? Well, no. Unfortunately, all of this pales in comparison to the emissions created through the process of manufacturing the phone itself. It brings us up to over 100 million tons of CO2 per year for the world's smartphones. So clearly, we have a lot of opportunities to reduce our smartphones' impact on the environment.
Okay, hold on, I got to go ahead here. So that was the edge AI. What about what about just kind of the data center area? How big is this? So again, we're going to explore just how far this is off with this claim. The first claim that came from 2018 by the same Karen Ho who did the Empire of the AI book last year had this paper on the MIT Technology Review, training a model in 2019, a relatively small model, as much carbon as 5 cars in their lifetimes. And that was up in the cover of IEEE Spectrum, IEEE's flagship, predicting in 3 years after the article that it cost $100 billion to train a model on its most carbon emissions in New York in a month. And that was trumped by people who said by 2026, it was going to cost $20 trillion to train a model. So where did these numbers all come from? In fact, when these things came out, I asked my friends in AI, "Are this stuff true?" And they didn't think it was true, but nobody had any data, which got me started on this journey. So we all know there's training like sending your kid to college, inference is like after they graduate. And then Google published this paper to look for a more efficient model. This search for more efficient models called neural architecture search to try and make it more efficient and cheaper. So how often do you do these searches? Until you find a better model, then lots of people use it. So this result of this paper was called Evolve Transformer, but it didn't include any energy or emissions data. It just said, here's our results to find a more efficient model. So even back in 2019, people were worried about the carbon footprint of AI. So the University of Massachusetts did a study on what was the emissions of the search for a better model. But there were some mistakes in the paper. The 4Ms I talked about earlier, they got them wrong. They use public data. They didn't use actual Google data, so that was off by a factor of 5. That's kind of understandable. They didn't ask for it, but they didn't have it, so they did it themselves. Unfortunately, they didn't understand how these searches are done. And maybe in the old days, you would use a full-size model as part of the search, but that was very expensive. It was tremendously more efficient to have a small proxy, much simpler model to explore the space. And then when you find something interesting, you'd use the full model. So actually, that made it another factor of 19 too high versus reality. So far, it's almost a factor of 100 too high of what it was really like for Google to search. Unfortunately, many reporters, including Karen Ho, got confused of what this paper was about. Was it about training a model or searching for a model? So they thought it was training the model instead of searching. And searching is 1,300 times higher than training the model found in the search. I mean, probably not surprisingly. So you multiply those three factors together and you get 120,000. So what common perception was 120,000 times higher than what it really was for Google. So that meant 250,000 kilograms, according to that miscalculation, was actually 2.5. So instead of 5 car lifetimes, it was this tiny sliver of a car lifetime. So what do? That paper appeared at the conference. We tried to publish a paper to correct the record. And, it's doing okay. You can see it went from 36 over 4 years to 500, not bad. But the original flawed paper is up and to the right. 6,000 citations. I think I've only got, over my 50-year career, only a couple of papers as high as citations of that. So it's very, very hard to correct the record once a paper comes out if it's got a miscalculation. Okay, so AI is the biggest environmental problem in IT. We've got enough data now, we can figure it out. So let's go compare these things. So the AI of data centers was this 18 million tons. The phones, the embodied part was 72 million tons, and then we could show how much of that is operational for data centers, right? The hardware operational things, big part, not the embodied, but we can estimate that. And AI, again, is only a piece of what's going on in the data center. We published papers a few years ago that it was 15% of Google, maybe it's 25% now, but you pick your number. But basically, the embodied carbon emissions of phones, 1 billion a year that we use, is order of factor 15 higher than the emissions from data center AI. Okay, so the final pitfall before we go to questions is ignoring AI's upsides. And, it can be a big mistake to ignore AI's downsides, but it's also a big mistake to ignore AI's upsides. So my favorite example was done by Google. Here's one AI result that talks about carbon footprint. So aviation is one of the largest sources of global energy. It's responsible for about 2.5% of all emissions. And for more than a third of the emissions, amazingly, is the contrails. So those streams behind jets that come along, it's the contrails that are a part of the carbon footprint, besides just the burning of the fuel. But contrails only happen when you fly through humid regions. So Google people figured out if you predict paths, you can go either higher or lower or avoid things and avoid the humid regions and reduce your contrails. Well, how effective would that be? Well, they did this study with American Airlines that it's 70 test flights over 6 months. And they found they'd only have to increase the emissions fuel by 0.3% to reduce the emissions and how reduce the contrails. And how much could they reduce it? They could cut the contrails in half by burning a little bit more fuel, making it a little bit longer flight. For 2023, it's 950 million tons of carbon emissions for aviation. So if a third of it, we can get rid of half of a third times 950 tons, that's 180 million tons of carbon emissions. So keeping that in mind, right, that's 40 times larger than hyperscaler or data center I used for 2023, and 2.5 times bigger than the smartphone embodied emissions. So just that one AI result can potentially do that. Okay. And so like this, yeah, so I think the current issue of communications ACM, we have an article talking about the impact of AI. And one of the bottom lines is a big mistake to ignore the upsides, is ignore the downsides. So let me wrap up and before we go to questions. So this, you can break emissions into these four pieces. The first three calculate the energy, and the last one turns it into emissions. And optimizing them can really, realize the amazing potential of AI in a sustainable manner. Rather than this misleading unbundled energy certificates, let's try and use local energy 24 hours a day rather than playing games with it. Not only should hardware people think about performance for total cost of ownership, but also for data center power and carbon emissions. And, global emissions is a really important issue, but we got to get the numbers right to make sure we work on the most important problems. And with that, I'm open for questions. And I think we can have time for them and still stay online.
Thanks, Dave. Have you looked at the Colossus 2 from Elon? And
What?
the
Colossus
Elon Musk
2?
XAI is a Colossus 2 data center with, bajillion natural gas turbines.
Well, yeah, that's the OpenAI. I can't.
XAI.
Yeah. So yeah, natural gas is a disappointing energy source. It's better than coal. That's about the only thing you can say for it. Yeah, I'm hopeful that companies will take their environmental footprint seriously and try and use clean energy sources to be able to reduce their carbon footprint. I think like the good news is I've been given this bad AI talk for maybe 6 months. Microsoft said we're going to stop using these unbundled energy certificates. We're going to stop doing that anymore. And actually, they're revising the greenhouse gas protocol because they want the market-based thing to mean something. They're getting rid of this unbundled EACs, and they're going to try and do it. You have to use the energy in the same hour, and you have to be potentially connected to the energy source. You can't get credit for something, it's other part of the world. So we're making movement kind of as an industry towards having better metrics. But it's up to companies to decide if they're going to follow best practices and reduce their footprint or not. But we as consumers can affect this, right? Especially since it makes a lot of sense to do things in the cloud. You can favor data centers that are in locations that have very clean energy or reduce that. So I would certainly encourage those of us who are doing work in AI to ask questions about where the jobs are running and how efficient is the 4 M's, how efficient in terms of the hardware in the data centers, and then how clean is the energy that's supplying them. Right.